So what I need to talk about a little bit is population size, because this is going to be really important in building the health of your aquaponics system. And I think what I should mention is that that really your aquaponics system, I hope some of you realize this, but maybe you don't know this yet. Your aquaponics system is really like a microcosm. So it's like a mini ecosystem that simulates a lake or a pond or a stream. And so that's what we need to know is that what we're doing in our tanks or in your designs, your second round prototype design, is you're trying to simulate this microcosm, but control it in a way that gives us the maximum amount of things we're looking for, so vegetables and fish. And so what we're probably going to do is spend some time coming up soon. We're going to go study the snake den branch that leads into Lake Thoreau or Audubon, I forget. My geography gets a little mixed up. But it's the stream just behind the school, and we'll study it for some of the things that you need to be taking into account for your aquaponics system, and so it'll help us emulate what's going on out there, which leads to high amounts of vegetation and fish in the lakes. So just that's an aside, but as far as population size, I think it's important to define population one more time. And this is a group of individuals living in the same place, and belong to the same species. And that in itself is another term to define. And I'm just going to write it. We've already had this discussion, so I hope that you remember this, but I'm not going to go into a lot about this because we've already talked about this in class. This is a group of individuals that can, not necessarily that they do, but they can reproduce and make fertile offspring. And that in itself means something. So I'll leave it there. So what accounts for population size? And there are four major factors that we think about. So I'm going to do my best to draw a circle here. Okay. And what we'll do is, what we're really doing is kind of making a diagram of these four factors. So if we label this circle as population size, there are several factors that influence the population size. So one thing would be births, which is sometimes referred to as natality. Natality, not fatality. You know the fatality would be the opposite, but natality, you've heard of like prenatal care. This is before birth care for pregnant mothers, so and for their babies. So this is natal means birth. And the other thing that can add to population size is immigration, which you should know is basically individuals moving into a place. And then we've got ways to reduce the population, which would be death, or sometimes referred to as fatality, but in this case, mortality. And we've got emigration. So you know the word migration, which means to move. An immigrant is someone who moves into a new place. We often don't use the word emigrant, but that just means to reduce in the population. So or to leave the population. So these are the four factors, and you should understand how they play with each other. So if I told you that there was a high amount of births, there are more births than deaths, but there was more emigration than immigration, can you make a prediction about the population size? Or do you need more information than just relative values, that one is more than the other? So that's what you need to make sure you understand, but that's not really the whole thing here. So I hope that you remember that we have two types of curves. I hope once I draw these, they come back to you. We have what we call the J curve, which I'm actually going to do. I don't know if you can hear my son there. He's fighting bedtime. So that's the J curve, also known as the exponential growth curve. And if you know what your, let's say for example, I know if you know y equals x squared, we go to exponent. This is the part of the parabola in the first quadrant, but there would be an equally matching one over on the next quadrant. But that's not what we'd see in reality when we're talking about positive values, right? So this is the exponential growth curve, and the assumption here that as a population would grow this way only if there are unlimited resources. So there would be unlimited amounts of births and immigration because there's unlimited resources like food, space, water, etc. And there's really fast reproduction rates. But like I said, this is never really the case, unlimited resources. So what we have instead is this curve, which you really need to understand and be able to explain and annotate. So we start off similarly, but then it plateaus. And so there are three phases here. The first of which is sometimes referred to as lag phase, but really it's like up through here. So this is the exponential growth phase. Oops, I can spell growth. That's not what, there's no P in there. The exponential growth phase, which actually looks very similar to this part right here, right? So it exponentially grows. Okay? The second phase, where actually you can see that the curve actually turns the other way, is the transition phase, or transitional phase. And you start to see that the population is starting to slow down its rate of increase. And then at the very top, we have our plateau phase. Plateau phase. And I think that's pretty self-explanatory, plateaus. So very quickly, when there are not a lot of individuals in a place, like, for example, low amounts of bacteria in your aquaponic system that are going to be really important for converting ammonia or ammonium into nitrites, and then into nitrates for your plants, the more you have, the better, right? So you need to make sure there are plenty of resources available for them, which would be food, which in this case would be the ammonia. They need lots of space or surface area to grow, and they've got plenty of water because they're in an aqua environment, in a hydro environment. So early on, when there are a few bacteria, they can grow really, really quickly, given they have everything that they need. But then once these resources start to become limited, the rate of increase starts to slow down. And then once they hit this top part, they're hitting their maximum number of population that can be supported in that environment because of the limited resources. Now, if they happen to get more resources, then this plateau phase would actually just move up. Or if they lost some of their resources, it would come down. And that's true for predator and prey relationships too. If this was one population of wolves, that feed on rabbits, then if there were less rabbits, then the the height of the plateau phase would actually come down. If there were more rabbits one year, it would go up. And this phase right here, if we drew a horizontal line all the way across to a certain y value, and I didn't label my graph here, but this is population size. This value right here on the y-axis is called our carrying capacity. Our carrying capacity. And really what that means is the maximum number of individuals that this environment under these conditions can support. And if we were to zoom in on this section right here, what we would actually see, I'm going to scroll down a little bit, is it going up and down over top of and around the carrying capacity. As there are a few more births, there are more individuals than the environment can support, so some die and the population comes back down, but now there are less individuals that the environment can support, so there's some more reproduction that happens, and it continues to go back and forth. And it wavers around the carrying capacity. So you really have to look at what the trend is for that carrying capacity, not what the actual values are. And that's key for being able to answer some of these questions. And I think, oh, and you have to be able to know what some of the limiting factors are for this carrying capacity. So I mentioned some of them, some availability of some resources such as water, food, maybe even sunlight, depending on what kind of population we're talking about. We could be talking about plants. Shelter, space, or amount of oxygen. If it's a fish, it needs a certain amount of dissolved oxygen, or anything else that lives underwater. Or one of the limiting factors could be the buildup of waste, or as excrement, feces, or the amount of carbon dioxide will limit the amount of individuals that can survive in that environment. Again, like I said, predation. And the other thing is that when we get more, as we get more and more individuals in our population, they get more crowded, which means that there's a higher chance of the spread of disease. There are more individuals that are coming closer into contact. Some of these viruses and bacterial infections have an opportunity to jump species and spread much more quickly because there are just more people around. Or not even just people, other individuals or organisms, okay? So I hope that makes sense. I'm going to stop there. I hope that was detailed enough. I want you to think about how this might be, what's going on with your bacteria in your system. And we're going to do our best to try to model this by collecting samples of your bacteria and growing them on petri dishes to see if we can count the number of colonies and see where your population is in your system. Maybe we're going to see over time it's going to move towards the plateau phase. Maybe it's already at the plateau phase. Depending on where you got your water source, we might have different kinds of graphs. Okay, I'll leave it there.